about the formalism, like the mathematical formalism of quantum theory, in particular quantum information theory. And then we talk about applications, like what can you do with this theory? What interesting phenomena arise here, and what kind of tasks can you achieve with quantum information theory, especially also in contrast to classical information theory, like what's different in quantum. Okay, so let's start with the classical part. First, back to the classical information theory. Of course, if you have any questions throughout the lecture, just ask. I don't know what like all of your backgrounds are, so if something's unclear, just let me know and then I can explain it. So, okay, the question that classical information theory is trying to answer is like, what is information and how can I quantify it? Like, how can I build a mathematical theory to describe information, which is a very abstract concept. So, if I give you an example, say, you look at a coin toss. So if you have a coin and you like toss it, you have two possibilities what could happen. Usually, like either it lands on heads or it lands on tails. So the possible outcome of this little experiment are heads and tails. And if you have an ideal coin, which is like shaped in a way that heads and tails it's basically identical, then the probability that it lands on either of these outcomes is the same, like it's 1/2. So the probability for each outcome . So suppose now, like you take a coin and you flip it and it lands on heads. What have you learned, or how much have you learned? How can you like answer this information? What is the amount of information that you have learned? This is basically the question that information theory concerns itself with. Like, how can I assign numbers to these experiments? How can I quantify that? Sometimes I learn more than in other cases. Because a priori, like from our daily life, there's no good intuition, like what number you should put to this question, how much information have I learned? But you have clearly some intuition for, in some situations I learn more than in other situations. For example, if I have a coin that is biased, where I don't know, it lands on heads in 90% of the cases, and on tails only in 10% of the cases, and then I flip it, and it landed on tails, like the less likely outcome. This is somewhat like a more surprising event. So we'll get back to that. So to understand like how we can quantify information, the first ingredient that we need is probabilities. Because all these kind of like experiments that we discuss, it's about situations where the outcome is not certain, where you can say something about how likely are certain things to happen. Let's talk about some basics of probability theory. The central concept that we need in probability theory is that of a random variable. So that's the object that describes experiments such like a coin toss and captures that like we can't decide in the beginning what's going to happen, but we can assign probabilities to different outcomes that are going to happen. So random variable. Like it's a formalization of an object that allows us to describe like events or processes that depend on random aspects, let's say. And generally it's a triple. Big X, capital X, curly X, and E of X. Where the capital X is basically like the name of the random variable. So in the example above, there would be like, I would say X is the coin. And then the curly X is the alphabet of the random variable, so the possible outcomes that can happen. And an element, like this is a set. For example, if we had here, so my example was heads and tails. And an element of this set, like I have a little x, so that's a small x and that's a capital X. Just hope it's clear from context. Always. So one element of this alphabet I also call a realization of the random variable. And the last element that we need is the probability distribution that describes how likely the different outcomes are. Over the alphabet. So it's a function that takes the alphabet and maps to the interval 0 to 1, such that they all sum, like all the elements for the elements in the alphabet sum to 1. Okay. That's like the central object that we need to describe our experiments. And now if I have not just one random variable, but two, for example, I have 2 coins that I want to flip, then I just have multiple of these triples that describe the individual elements. So I have 2 random variables, so I just have 2 triples, say x is px and y. And now when I want to talk about them jointly, I can define the joint random variable. Then I would have a triple, I don't know, whatever I want to call it. And the alphabet is then simply the product of the two, so I always have to take a tuple of elements. And I have a joint probability distribution. But this joint probability distribution is not necessarily the product of the individual probability distribution. So since p x y is not necessarily px times py. This is only the case if the 2 random variables are completely independent. To describe the joint probability distribution, I need to know more than the individual probability distributions. I need to know how they are correlated. So I need some additional information to be able to describe this joint behavior. Okay. Okay, I have a question for you. This a random variable, for example, of a coin. Does it describe a property of the coin? Like, is it an intrinsic property that this coin holds? Yes?
I believe we're assigning it.
Yes, we're assigning it, maybe based on observations or something. Yeah.
But then you have to get the nitty-gritty of statistics of Bayesian this frequent is that. Is it
Yes,
your belief of it?
Another discussion, yes. Maybe if I give you an example. So let's say I flip the coin and I hide the outcome. Then like this probability distribution exactly describes for every one of us how we would assign the probability of getting heads or tails, right? But if I flip the coin, I like hide it from you, but I look at it. Like, this probability has now changed for me. Not for you, but for me. I now know for certain what the outcome is. So in the end, this probability distribution describes the knowledge that someone has about the coin. Like if I get, like in this example, I have more information than you, so for me the probability distribution has changed, and you have a different probability distribution, so you have different knowledge. That's what we should keep in mind, that when we talk about probabilities, and later also like quantum states and everything, it's a subjective description of the person who describes the experiment. Yes?
Why has your probability distribution changed? Didn't you just get a certain realization of the outcome, but the probability is still a 50-50 every time?
But the probability that this particular coin shows heads.
Got you. Yep.
Yeah, it's not a statement about what happens if you throw the coin, but that this particular coin has this value. So, yes, so with probabilities, we want to like capture the knowledge that we have on describing events and processes. Okay, and this can change when we get more information. So generally, it's useful like to capture side information properly. So it can happen. We have side information. About the like, random variable. Okay. So let's make an example for this. So suppose someone gives you a die. So like one die with 6 different sides, 1 to 6. Someone hands you a die. And you know that it can either be a fair die, where all of the 6 outcomes are equally likely, or it can be a biased die. And yes, the biased one is such that it always shows a 6. This one. You don't know which one you got, but each of them, like both of them, is equally likely. Getting the fair die, this 1/2, it's like the probability of getting the biased one. Okay, so clearly if you learn which die you get, it helps you to guess better what the outcome of throwing the die is, right? add, like this. Let me make this precise in terms of the random variables that we talked about. So here you have a die. This one is described with a triple x dx. And here, you know, like x is the die. The alphabet is the same for all of them, 2 to 6. But the probability distribution, you don't know exactly which one it is. You know, either it's the one of a fair die or it's the one that shows always the 6. And which die you have is the second random variable. So this one, the decision which of the two dies it is the second random variable. So y. P1. So this is either fair or bias. And here we know the probability. So this is the probability distribution. Now we have two random variables, one that describes the object we're interested in, and one that describes some side information that we have. Now as soon as you learn the side information, you can decide, you have more information about the actual object you want to describe. So, as you learn y, you know more about so you get this conditional probabilities. So probability x given y is the probability of an outcome of rolling the die given if it's fair or biased. So let's say, for example, that it's fair. If I already know that I have the fair die, then I know that the probability of getting each of the possible outcomes is equally likely. So this is 1/6 for all x in the alphabet. And in contrast, the probability distribution, if I have the bias die, it's biased such that it always shows a 6, well then the probability distribution is a bit different. Probability is 1 for 6 and 0 else. Yes, and this is how we can capture side information about the object we're interested in, that itself has some uncertainty, like that itself comes with the probability that certain events happen. And then some useful relations between probability distributions. The biased, the conditional probability distribution, I can also get it from the joint probability distribution divided by the marginal probability distribution of the thing that I'm conditioning on. And I can rewrite this to changing the conditioning. Some nice mathematical relations that we need to calculate. So the latter is also called base rule. And one comment on the notation, we also, like here, the index of the probability distribution is the random variable. and the argument of the probability distribution is the realization, but sometimes we leave out one of those because the information is a bit redundant, and typically it's clear from context what is meant. P just with the index or just with the time range. Okay, so far so good. So now we've discussed how to talk about probabilities and how to capture side information with probabilities. Now we want to talk about how do we actually quantify information. How can I put a number to the information that I learned when I do an experiment like a coin toss or throwing a die. Do you have any questions so far? Yes?
When you write on the top of the fraction, p, x, y, is that just the multiplieds? Is that as if they were independent, or is that?
I mean, this one?
Which means the one at the top in the numerator.
Yeah.
P underscore,
Yeah.
It's not necessarily the product of the two.
Okay.
It can be different. I can't directly get it from the product alone.
Yeah.
So it's just
Joint.
the joint probability distribution.
And how would we? I'm confused about then what the difference between that and the left-hand side of that is.
This one?
Yeah.
This one in the end is just the probability distribution over x. Okay. You can see here in the example, I just need to say what it is given the value of y, how does x look?
Whereas that one is combined.
Yes, exactly. It's I take all possible tuples and get the. It's like this one is how surprised am I to see x when I already know y,
Yeah.
and this one is how surprised am I, or how likely is it to see a tuple of value.
So that's more possibilities in that one versus.
I think in the end it's the same number of possibilities.
Okay.
But I mean, you can see also here how it's related. To get this one, I have to take the conditional entropy and multiply it by the probability to get y. Because while this, I mean, it has the same number of possibilities, because I have to take all the tuples, but the probability of getting y in the first place is not represented in this one.
Yeah, that's why I thought it would have more on the other side, because you'd have to take into account the probabilities of getting y, but I see, yeah.
I mean, this one here, if I take together all the possible probabilities that I have to specify this conditional probability, it's also 6 plus 6, so 12. And if I look at the joint probability distributions, I have 2 times 6 possibilities also. So it's the same number if I specify the whole object. It's just the probability that y appears in the first place is not present in the conditional entropy. So now what we have quantified with the probabilities is how likely events are. But now we want to have a measure of information actually. How much do we learn when seeing these realizations? That's the next part. Here we'll talk about entropies. Entropies and information. So this is about why are we sometimes more surprised than other times? So if we have these two different dice, then case that we have the bias die, okay, this one is a bit trivial. I mean, this just always shows a 6. But in this case, with the bias die, if we see a 6, we're not surprised at all, because we know like the general structure of the die, so we always expect already a 6. Whereas if we have a fair die, it's like if we see a 6, we're like, oh yeah, okay, this was not impossible, but we have many possibilities, and this is just one of them. So the less likely an event is, the more surprised are we to see the event actually happening. If in the case of the bias die we would see something else than a 6, we would be very surprised. We would basically be infinitely surprised because it's not supposed to happen at all. So the measure of information, like, when we talk about information and surprisal, they are very closely related. Because we say, okay, if an event happens that's very likely, we don't gain as much information. For example, if we see the event in the bias die that we got a 6, then we actually didn't get any information at all, because we already knew before that it will show a 6. So if we have a deterministic event, this doesn't give us any new information. Okay, so the measure of information should capture that less likely events give us more information. So, also say is more surprising. Okay, now I want to capture this with like numbers. So to come up with some function that assigns a number that quantifies the surprise or the information, given the realizations of our experiment. So, yeah. I'll give you a definition called the information content of a realization. As this function is called I of x, and it's given by minus the logarithm of the probability of x. And if you plot this, why is this a good way to capture information? You see, like, what desirable properties it has for capturing information. Yes?
Well, as you said, the less likely an event is higher.
Yes. This we directly see. If it's a 1, then like this is supposed to go to 0. And if the probability goes to 0, then it should go to infinity. Because if the probability is 0 and I still see the event, then, you know, infinitely surprised. Yes?
I think the most important one, more important than even that, is that for mutually independent events, the information is linearly summable.
Yes, that's true. Yeah, we have probability distribution, like learn probability distribution for independent random variables, we will get that this information content is additive. Let me capture these probabilities. These properties. We said the less likely events are more surprising. It means that mathematically it is monotonically decreasing. Using the logarithm, and you can see four independent variables. You see, you take the information content of two realizations, and you take the joint probability distributions, x1 and x2. And then it's simply the properties of the logarithms that are used to. So the independent, this probability distribution factorizes, so p of x1 times p of x2. And then I just get the sum of two logarithms. So the information content plus the information content of x2. Are there more? Yes?
Yeah. Just to clarify, are you taking the logarithm in base 2?
Ah, sorry, yes, I should have had it. I mean, at this point, it's actually, yeah, okay, yes. To get the 2 here, the number 1 here, it's to base 2. But the general properties would be the same for other bases. Information theory, that's a natural choice to take the logarithm to base 2 because we always talk about bits. And then base 2 is the natural choice. I also had a discussion with a colleague of mine who's like more a physicist. And he always takes the logarithm to base e because that's for him the natural logarithm. But in the end it doesn't matter because they only differ by a factor. So in everything that you calculate with the logarithm, well, you have to account for this constant factor in terms of the actual numbers that you get out, but qualitatively the results are the same. Okay. Are there more nice properties that this function for the information content has?
Always positive.
Sorry?
It's not very important, but always positive.
Yes, it's a non-negative number, which makes intuitively sense if I say this is how much I learn or how surprised I am. A negative, like you can't really learn negative information. I guess you can forget something, but it's not so easy to properly quantify mathematically. Come up with an experiment where you would do something like roll a dice, see the outcome, and you have less information afterwards. So it makes sense, it's non-negative. Can you see more? It's concave. Is this strictly necessary for?
It's useful. But
it's useful. Yes, that is true. It's true. suppose I had a function where, I don't know, let's say at probability 1/2, like here, I get 1 bit of information, but at probability like 50.0001%, my information is 10. Would that be intuitively useful?
Continuous.
Yes, yeah. It's continuous, which is nice because think, okay, if something is just slightly more or less likely, then the information content should be roughly the same.
Sorry, might be a dumb questions, but I thought concave was the opposite direction because it makes a cave.
Oh yes, it's back to convex.
Oh wait,
Yeah, you're right.
Words are difficult.
I didn't think about it. Good catch. Yes, I have one more important property of this function. Doesn't matter, like if let's say I have an experiment with a coin where heads or tails are equally likely, or I have an experiment, I don't know, where I don't know, what can I do? So like, I take a book and I let it fall down and either lands on the front page or the back page with equal probability. Are these two experiments different? No, right. And I mean, of course the random variable is different, like I call it differently, the alphabet is different for the two, but what's not different is the probability distribution, and that's the important aspect for the information content. So this function only depends on the probability of these realizations, but not on how I call these realizations. And last part is only depends on the probability. So these are like all nice mathematical properties that show that this is a good choice of function to capture, like quantify information. And in fact, what you could also do is like write this the other way around, start with all these properties that you like, and then you will come up with this is the only possible function that does this. Like you need a logarithm, you need a minus sign, so you can derive it just from the properties that you would like it to have. So this is really the only possible choice of function for information content if you don't want to give up on any of it. So now we've quantified how much do we learn when seeing a realization of the random variables. So I can now say, okay, if I see heads, this is how much I learned. If I see tails, this is how much I learned. If I roll a die and see a 1, this is how much I learned. But what we also would like to be able to describe is how much information do we learn when performing the experiment, without specifying which random variable I see. How much do I learn on average when just doing the experiment of tossing a coin? Here's the general amount of information. From a random variable. For this, we just take the expectation value over all the realizations that the algorithm has. The Shannon entropy. expectation value, we take the sum over all the realizations, multiply it with the probability. This is the expectation value, the information quantity over all the realizations of X. One thing we have to be careful about with this formula that we have here is what happens if the probability is 0 in this case. Because in that case, we have 0, the logarithm 0 goes to infinity, so we have 0 times infinity. But in that case, what we check is if you take this function here and let the probability go to 0 and calculate the limit, you see that this is 0. X times the logarithm p of x. Which also makes sense in the context of this quantity, because if the probability is 0, we don't want any contribution from this to the knowledge that we get. Okay. So you can see, if you now take the example of the coin toss again. Likely outcome for both of them. Then you can calculate this Shannon entropy. We're just putting in the number for the probability distribution. So just have minus 1/2 log 1/2 minus 1/2 log 1/2. And if you do this calculation, what you get is 1. So when tossing a coin, you get exactly 1 bit of information out of that experiment. If the coin is an unbiased coin. That means that so it also in turn tells you, okay, if you say that something is 1 bit of information, that means that you learned 1 possibility out of 2 equally likely possibilities. As soon as you have a biased probability distribution here, then the amount of information that you learn will change. Okay. And now based on this Shannon entropy and the different probabilities that we discussed, you can also come up with other entropies. So let's just define a few more useful entropies. So we take a few random variables. X and Y. and take pxy with their joint probability distribution. We can just define a bunch of interesting other entropies. The first one is just the joint entropy, which is very straightforward, taking the formula for the Shannon entropy and just replacing the probability distribution with the joint probability distribution. And the sum over x and y. This. You can also take the conditional entropy. Which is supposed to tell you how much information you have about x when you already know y. So analogously to the conditional probability distribution. This one is given by the joint probability distribution times the logarithm of the conditional. And this one can actually be rewritten as the joint entropy minus the marginal entropy of y. And the last thing to define is the mutual information. This is denoted I, x and y. We use a different letter than h because it's not exactly an entropy like this one. This is the entropy of x plus the entropy of y minus the joint. So the Shannon entropy as we define it there, this is supposed to tell you how much information do you gain on average when doing this like experiment that corresponds to the random variable. In the joint entropy it tells you, okay, how much information do you gain when doing an experiment that is described by the two random variables. The conditional entropy tells you how much information do you gain about x when you already know y. But then the mutual information tells you how much information do x and y share, like how much do they have in common.
Sorry.
Yes.
In the conditional entropy, shouldn't it be the probability of the conditional probability?
You mean the first one?
Yes.
No, in this case, because if you like derive it similarly to how we derived the Shannon entropy, what you would say is this information content function would be minus log of the conditional probability, and then you take the expectation value over all realizations. And for the expectation value, you need the joint entropy here. Okay. You can very nicely visualize the relationship between these entropies by drawing a little circle. So, this circle describes h of x. Circle that describes h of y. So there can be some overlap between the two random variables. If the random variables are independent, these two circles wouldn't overlap. They would be completely separate sets. And then you can add these other probability distributions. So the like union of these sets This would be the joint entropy, so it takes all the information that is present in both of them. It's getting a bit messy in terms of colors. So, if I take the area here, that is h of x without the overlap, this would be the conditional entropy of x given y. As you see, you already know y, so you already know this part about x, and you only learn the rest of it. This also fits well with this formula here. That's the conditional entropy of x given y is the joint entropy minus the entropy of y. Exactly, you take the whole thing and take away h and y, then you're left with the rest of this circle. And you can similarly do it for the other side. Then you would get h of y given x. And the mutual information this part. You can also see that from this formula. Because if you take h of x and you take h of y, then the part that overlaps, you have it twice, right? You have taken this circle and you have taken that circle, so the part that overlaps appears in both of them. And if you only want like this mutual information, this overlapping part once, let me visualize this. So in this formula, what happens is you take h of x plus h of y. But in the end, you want to get out this overlapping part. And now you remove the joint entropy, which was this thing that entails both. So what's left after this is just once the overlap between them. Because you have removed each of those things. Once the overlap remains. And that is the mutual information. That's like a useful way to visualize how these things are related. And we'll later also see how these entropies, in the like quantum case, come to play in certain applications where they're useful to like quantify how well we can do certain information processing. Then I want to do an example. Okay, suppose we have some sort of box that just spits out bits. You know the general behavior of the box, like the structure that it has. So it spits out bits one after the other, and the structure is that it's always like 2 zeros followed by a 1. Okay, so now we know what the box is doing. Now someone hands us the box, and like we need to predict what the next bit is that the box will output. So in the beginning, when the box, let's say it has a little bar. And every time we press it, it outputs 1 bit. So in the beginning we get the box, we haven't seen any bits, we haven't pressed the button yet. How much information do we learn when seeing a bit? That's what we're going to quantify. Okay. So the question is, how is our uncertainty about the next bit quantified? Okay, and the first scenario is that we haven't seen any output yet. So what's the probability that the output will be a 0? So we know the general structure of the source, like the general behavior, what it's doing.
2 and 3?
2 over 3, yes. Because we know like a 1 is less likely than a 0. Like the 0 appears twice more often than the 1. So if I press a button, it's more likely that a 0 will appear. The probability of 0 is 2 over 3, and accordingly, probability that it's 1 is 1 over 3. Okay. So this we get from just knowing the general behavior of the box. And if we quantify this in terms of the Shannon entropy, like how much information do we get when pressing the button and seeing 1 bit, we just have to plug in the probability distribution. And if you do that, it would be minus 2 over 3 log 2 over 3 minus 1 over 3 log 1 over 3. And if you put this into your calculator, this is roughly 0.918. So you can see it's different than the coin toss that we had for the fair coin. It's a little less information that we get, because we already knew that certain bits are more likely than others. Okay, so that's the start. So in the beginning, this is how much information we get when seeing 1 bit of output from the box. Now in the second step, we have now pressed the button once, we have seen 1 bit. I want to see how does this quantity change. How does our knowledge, how does the information we get out of this box change? So now we have one known symbol. So we have some side information. It means now we have to compute h of x given y. So y is the next bit that we want to describe. So how much information we get with the second bit, and y describes the bit we have seen. Okay. To compute this, we have seen the formula. This one. We can rewrite this a bit using the relations that we had in the beginning about probabilities to get a more useful quantity out of it. Because the issue with this formula at the moment is that this joint probability, we don't know this. So but if you rewrite this from the beginning, we get the probability distribution over y, then the conditional probability distribution of x given y, and the logarithm of this conditional probability distribution. Yes. Okay, So there are two probability distributions that we have to specify to be able to calculate this property. Do we know the probability of y? So what is the probability distribution for the bits that we have already seen?
We specified it above.
Yes, it's exactly the probability distribution here, because that's where we got the bit from. It's probability distribution for getting a bit without having any prior information. So this is the star. Okay, so we need to see how does the conditional probability look. Specify all the cases that can appear. So x equal to 0 and x equal to 1, y equal to 0 and y equal to. So let's say the first bit that we have seen is 0. What is the probability that the next bit is 0?
50-50.
Yes, now it's 50-50. This is 1/2 and this is 1/2. Because if we look at this structure of the box, you know that if the first bit is a 0, we're either in this position or in this position. That means both positions are equally likely. So the next bit is either like getting a 0 or 1 is the same probability. If the bit that I've seen is 1, what's the probability that the next bit is 0? 1. Because then I know exactly I'm at this position in the bit string, and it has to be a 0. A 1 is never followed by another 1. So from knowing the structure of the box, we could come up with this the conditional probability distribution. So now one can take all these probabilities, put them into the formula, and calculate how much information we get when seeing the second bit of the box while knowing the first one. And if we plug in all the numbers, then what you get is 2/3, so roughly 0.66. So uncertainty about the next bit has decreased by learning 1 bit already. Okay, so the third step is now we have 2 known symbols. So okay, if we have 2 known symbols, like we need to do again the same calculation. If you look now at the conditional probability distribution, like the possible values of y that could have appeared, now 0, 0, 0, 1, 1, 0. 1, 1 cannot appear because the structure of the box doesn't allow that. So what happens in this case? Like, if I already know 0, 0, what's my probability of seeing a 0?
Impossible.
It's impossible, yes, because with the structure of the box, we know a 1 has to come. And you see with the other probabilities, it's the same. If you already know 0, 1 has happened, then the next bit always has to be a 0. There's no other possibility. Has to be this one. So by knowing 2 bits, you already have perfectly determined what has to come next. From the structure of the box, knowing 2 bits, you can now completely predict the rest of the outcomes of this box. So now everything is deterministic. Which means if you plug this in to the formulas, you will get a 0. So there's no more information to learn. 2 bits is everything like you can learn from this box. After that, you can predict everything. If I have a box that just randomly output 0 or 1 every time. Will I see something similar? Like at what point could I predict the next outcome? You see, no. It's just impossible.
If they're jointly independent.
Yes. Because if you have a box that just in each run independently, randomly chooses a new bit, then there's no way, like, no matter how many bits you observe, we'll never be able to predict the next one. But with this one, there's a clear correlation between these bits, which at some point allows you to predict the answer. Okay. So the conditional probability, conditional entropy quantifies how your knowledge decreases, at which point you actually can predict everything. Okay, and then we come to the last aspect of information theory that I want to discuss before we start with the quantum part. And that's communication theory. So one aspect of it. So in principle, one can come up with many definitions of entropies. And people did come up with many definitions of different entropies. The one that we derived was we took this information content function and took the expectation value of it. But one other example would be, you take this information content function, don't do the expectation value, but for example, take the minimum over all probability distributions to quantify how much information do you get, what's the minimum of information that you get when seeing a realization. And this way you can come up with many possible entropies. But what's interesting is about these entropies, it's when they have an operational interpretation, so when they're connected to a task, when they quantify something meaningful. And one example for this is the compression of information. So usually messages, like if you want to say messages, they contain a lot of redundancy. Like especially our language contains a lot of redundancy. If I misspell something, then you typically can still understand what I'm saying. So I'll give you another example. For example, if I write down the following. Can you read this?
Yes.
Decrypt what it means. Yes, you got it?
Yeah.
You remove the vowel?
Yes, I removed the vowels.
But someone said was that just a question, do you understand it?
Who would say they know what sentence is written?
God does not play.
Nice.
Yes, exactly. And I just removed the vowels and left everything else in there. And that, depending on the sentence and depending what the structure of the words exactly is, it's possible to get the original message back without having the vowels. mean, I could have gone further and like remove more or exchange certain letters in addition. The question is, at what point does it become impossible to get the original sentence back from it? How much can I remove from the sentence in order to like still being able to get the original sentence back? And this does not only depend on the sentence, but also on some of the context, how it was created. For example, what was very helpful to you was that you knew it's an English sentence. If I like leave completely open what language it is, then the amount of possibilities is much larger, and it might be much harder to get back the original sentence. So this is some form of like compressing information in order to make it take up less space. So the way how information is created is a big factor in this. For example, in this example with the source here, the bit string that the source puts out. If I know it comes from this source, then I can compress this bit string to 2 bits, and from then I can get back the whole bit string very easily because I know the structure. In contrast, if I have a source that just randomly outputs 0 or 1 and chooses independently every time, then there's no way I can compress a bit string. Each of the bits is completely independent of the rest of the bits. Okay. And this is quantitatively captured with the entropy of the source. This is what's called Shannon's noiseless coding theorem. Basically says, suppose you have a random variable exists this compression scheme. It allows you to store these bits that the random variable outputs. Information to be stored using h of x is source x that outputs bits, and this would undergo some form of compression. And get a different y. And what the theorem guarantees you is that like there exists this compression scheme and the D compression. So you get back the original information. It doesn't tell you how to do it, it just tells you there exists one that allows you to compress it to an amount of bits per symbol that's given by the entropy. So it's here how this works. Let's look at one concrete example. Okay, so here's some tools. Okay. An alphabet that consists of 4 values, A, B, C, D, and some probability distribution. And it specifies with what probability the individual outcomes appear. And this is in order of the symbols, 1R, 1/4, 1/8, 1/8. Okay. If you just like ignore these probabilities and just know, okay, you need to encode 4 symbols using bits, then the natural choice is just to take 2 bits for each of the symbol and encode it like that. So, without any compression, we need 2 bits per symbol. To encode this. So A, B, C, D. A is 0, 0, D is 0, 1, C is 1, 0, D is 1. And then if you get a string of bits, then you can like uniquely identify which letter it is in the sequence, simply because you know each of them has 2 bits, and then like each pair is a unique letter from this list. So this would be like B, C, B, C, C. Okay, so this definitely works, but the question is, can we do better? Can we use less bits per symbol to encode this information? Because of course, I mean, communication is costly, so the less bits that we need to store this information, the better. And the Shannon entropy tells us how much bits we have to use to store this information. So what we can do is we can just calculate the Shannon entropy and then see if we can do better. If the Shannon entropy is 2, then this would be the optimal scheme. Then we need 2 bits per symbol. If you take the formula and plug in this probability distribution, like all the values, then what you get out of this is 7/4. So this is smaller than 2. That means there must be a scheme that is more efficient than this one. Like we need a bit less than 2 bits per symbol to compress this information. You have an idea what one could do? Yes?
So one could apply branching, so encode, since A has the highest probability, you encode A with 0, then you encode B with 1, 0, you encode C with 1, 1, 0, you encode D with 1, 1, 1.
Yes, so you use that. More likely symbols get shorter code words, because then if you have a long list of symbols, the short code words will appear with higher probability. So, to use 0, B is 1, 0, 1, 1, 0, and 1, 1. And this one, you can still see like every bit string that you come up with will still be uniquely identified. Example, this one, you see, okay, you have the first bit, it's followed by another 0, so this this one must be an A, because there's nothing that has 0, 0. Then you go to the next bit, this 0 is followed by a 1. So
1A.
it's still an A, yes? Okay. Then you have a 1, so it indicates it must be one of the other code words. And you can see how far is the next 0 away to identify which of them it is. And here you have 1, 1, 0, so it must be C. And then get the next one, this is 1, 0, and it must end here because there's nothing but zeros. That's B, and then we have another A. And now you can calculate how many bits per symbol do we have on average with this encoding. So to calculate that, it's a symbol in this case. On average, we would take the expectation value of all the realizations that you have times the number of bits that your code word consists of. And put that in, like for A, we see A appears with probability 1/2, and A needs 1 bit. This. And you go on, B probably appears with probability 1/4, but it's 2 bits. And then you have 1/8 times 3. Again, 1/8 times 3. Okay. If you take all of this and calculate this, what you get is 7/4. This tells you this is exactly what we calculated in terms of percent entropy, so this is already the optimal scheme that we can use. So this is scheme.
Question.
Yeah.
The theorem says that there exists a compression using this many bits per symbol, but does not say that it's optimal. Right? Or does it also like...
Yes, I mean, yes, okay, true. In the wording, it's not precise, yes. No, it means that this is the minimum you need.
Oh, so it's like the lower bound of...
Yes, it's the lower bound.
Okay.
Yeah, okay, right, the wording is not so precise.
I have a question about that.
Yes.
So this claim is that there's a compression scheme. You've also drawn a box for decompression.
Yes, so this is there exists a compression scheme that blah, blah, blah does this, that ensures that we're able to recover it perfectly.
Okay. But in your example with the bit strings, so you say that a 0 is A,
Yes.
but if you haven't observed any symbols yet, then that 0 that you say is A could have been the suffix of E or C, which also have zeros in them. So you can't say for sure. Like your decompression won't work perfectly.
Yes, so the situation, like the setting you're using this one is when you have a bunch of information, like a whole bit string, you want to send to someone, and to be able, like, you can of course just send the whole bit string, that will work, but in order to use less resources, you can compress it first and then send it, and the other person is supposed to be able to retrieve it perfectly. And in that case, when you already have the whole bit string, then you have enough data to do the scheme, like in this example.
So if the person who decompresses knows this is the start of the bit string,
Yes.
then they can
Yes, exactly.
decompress perfectly.
Yes, or another situation would be you have all this information and you want to store it on your hard drive, and like, you want to compress it as much as possible to use the space that you have optimally. Then, like, you know the start of it, you know the scheme, and just the question is how far can you compress it. Yes. You can also see, like, if you try to come up with more efficient schemes, where, like, one scheme that, of course, I could come up with. This is like, say A is 0, B is 1, C is 1, 0, D is 1, 1 also. Then you will see that if you like come up with bit strings of this, that these are not uniquely decodable, that there's some ambiguity of what it could mean. So this is really the optimal. Okay, so with this, we're like at the end of the first lecture, we covered the classical information theory part, and then in the next lecture we can continue with the quantum formalism. So now I wish you a good break and see you in half an hour. Okay, I think we can start with the second part of the lecture. Welcome back, everyone. So now that we have like seen classical information theory, we want to go to the quantum part, and for that, we first want to give a general introduction to the bits and pieces that we need from quantum theory. So maybe if you're a physicist and you've seen quantum theory or quantum information theory before, some of this might be a repetition, but in order that we're all on the same page, we're going to go through all the elements that we need. So the second part is want to be able to describe is the quantum mechanical experiment, let's say. What I want to be able to do is talk about preparing quantum states. Quantum state preparation. And some state design. The state then undergoes some form of evolution. So in this box, we see evolution. So after it has undergone this evolution, there will be a different state, side. And then finally, there will be a measurement. Will output some form of classical outcome. Maybe after measurement, we don't only want to talk about the outcome of the measurement, but also say something about the state after measurement. Call it 5. These three elements that in principle describe all kinds of experiments that you can come up with, or at least those that are relevant in our context. We want to talk about each of the three elements and specify how the mathematical description of these aspects is. Unfortunately, I don't have time to give you like the whole deep mathematical background of all of this. So I will just introduce the pieces that we need to talk about what comes in this lecture. So in particular, to talk about interesting applications of quantum information. So generally, our quantum states are vectors in a Hilbert space. So quantum states are vectors. Hilbert space H, and we always take a Hilbert space over the complex numbers. And what we need mostly in this lecture is the notation in terms of brass and cats. So we say vector in H is denoted like this. I wrote it up there. This is a cat vector. And then we need the dual vector for that. So we need the dual space, the dual space of H is H star, which is the space of linear maps. From H to its basis, you can see. And an element on that. Is denoted and you can see if this is a map from H to C, then if I apply it to a vector in H, I get a complex number out of it. So what we also need is an inner product on H. So we'll take two vectors phi psi. This inner product is this bracket. So some basic important concepts that we will need for these things. What we need to talk about is like how do we calculate inner product norms? Yes?
Sorry, is it the same phi in both?
Oh, sorry. Yes.
Okay.
This is supposed to be the same. So we need to be able to calculate like inner products, norms. We talk about a basis for the vector space. So you probably have seen these things like in linear algebra or something, but I will just repeat the notation.
Yeah, just support this.
Oh, sorry. Okay. So, if I have two vectors, so say I have 2D dimensional vectors. The vector is the entries, so A1 to AD. And psi 2. E1 D. So when I want to calculate the inner product, that would be psi 1, psi 2. And if I write this out in terms of these vectors, then this one. Take the complex conjugate of the entries of the first vector. Means if you calculate this, you get the sum from 1 to b of ai complex conjugate b I. this is how you generally calculate the inner product if you have two vectors. From this inner product we can get a norm. One. Given by the square root of the inner product of the vectorial itself. So we calculate that. If the norm is 1, then we say that the vector psi 1 is normalized. And another important aspect of Hilbert spaces that we need is that of an orthonormal basis. So normal basis H as a set of vectors. Denote them EI. So E goes from 1 to dimension of the vector space, such that, well, as the name says, they are orthogonal. That is J. Orthogonal, they're normalized. And every vector in the Hilbert space can be written as a linear combination of them, so they span the Hilbert space. Okay, so these are the basic elements that we need. Now we go to the most important kind of object that we'll discuss in this lecture, which is the qubit. Okay. So qubits, well, are generally the quantum version of bits. So there are two-level quantum systems, which means that they in some form generalize bits, but can do much more than classical bits. So two-level quantum systems. That means the Hilbert space is simply C2. Yes. And the one important part that we need about the qubits is the different bases that we can use to describe them. So the possible bases that I can come up with, say, I mean it's C2, so I can just choose two of them. So in this case, 1, 0 and 0, 1. And I denote them, first one is this 0 and 0, 1. So this is really the quantum version of a bit that can be 0 and 1. now, of course, we're in a vector space. So this is what we call the computational basis. Sometimes also call it the Z basis, because it's short. Of course, this is the basis that we can choose, but of course, the state of a quantum system is not only described by the basis state, but by all combinations that these states can take. So, the qubit can attain every typically normalized vector in C2. That means the general state of a qubit would be a linear combination.
Sorry, could you write a little bit bigger? It's just
Sorry, yes. Well, these coefficients, alpha and beta, are generally complex numbers, but they have to fulfill a relation for the vector to be normalized. The absolute value of alpha squared plus the absolute value of beta squared equals 1. Because then the norm of this vector is 1. That's one way to write down the general quantum state of the qubit. But of course, you can come up with other bases for this space. In principle, you have infinitely many bases to choose from. And one other basis that we always need, which is particularly nice, is the Hadamard basis. You can see. Plus and minus. The notation I choose here doesn't really matter in the end. I can call it whatever I want. Triangle is 1 over square root 2, 1, 1 over square root 2, 1. This is the Hadamard basis. It's called X basis. What we need about these two bases, in particular, their relation to each other. So, since it's two bases of the same Hilbert space, of course, we can express one in terms of the other. So, the relation. Calculate that, you see that you can express a linear combination of 0 and 1, to 0 plus 1 for the plus state and 0 minus 1 for the minus state. In this relation we will need a lot when we talk about how to measure these states. First, here, and define, okay, what's a valid qubit state? It's any linear combination of basis states. It doesn't necessarily have to be 0, 1. It can also be a linear combination of plus and minus. But it's important that these coefficients fulfill this relation in order for the state to be normalized. So in the end, a valid qubit state is any normalized vector in C2. Okay, so I have a question for you. So this, the following state, 1 over 4, 0 plus 2 over 5 times 1 a valid qubit state.
Squared is not 1.
Yes. Here's a condition, like if I take the absolute value squared. Take like 1/4 squared plus 2/5 squared. What you get out of that, calculate this is 13/64. So this is smaller than 1. It's not a normalized state in the Hilbert space, so not a valid qubit state according to that. And I have a second question. I give you psi depending on a parameter theta. Cosine theta 0 plus sine theta 1. This quantum state. For which values of theta is this a valid qubit state? Any value. Yes. You just square with this, you get cosine squared theta plus sine theta 1. So this is a valid quantum state for all values of theta. So as long as we're talking about these vectors in the qubit space, like this is basically the only thing you have to check. So this is what you would call a pure state. Let me make this Okay, so with this we can describe any state of a qubit. But what happens if we don't know exactly what state our qubit is in? Like, maybe we have some idea about what it's doing, but maybe like there's only partial information. So how can we capture that? This relates to the perspective that we discussed about probabilities. This object that we're looking at, it's about quantifying what we know about the system that we want to describe. So here we also want to capture that our knowledge might be limited and there's some insecurity in how well we can describe the system because we don't know everything about it. Okay. So suppose we know that the system is in one of several states. Okay, I want to do it more generally and not just for qubits. Actually, state the quantum system. So that the system of the states so 1, so 2, so the number of possibilities, so n. And I know what the probability is of these states. Call an ensemble of states. So if I have this insecurity about which state exactly it is, then I can capture this with a different mathematical object called a density matrix. You construct it summing over all the possibilities, the probability, and you construct object like this. So this object lives in the space of operators on the Hilbert space. This is a bounded linear operator on the Hilbert space. Down the former. So the density matrix, we don't take all possible bound linear operators, but we have some extra properties. So the density matrix is rho is an operator on H, such that the following three properties are there. It is normalized, so similar to our vectors we introduced before. But in this case now we have like matrices. Yes?
What is the cross and the absolute value?
Sorry?
What is the cross between the psi i's? Is it like
it's the case.
It's cat and brown.
Ah, sorry, yes. So this is like, maybe, yes. So this is a cat vector.
Okay, sorry.
So, yeah. And this is the bra vector. So we said like this was a function from the Hilbert space to the set of complex numbers. So you can see that this is an operator on the Hilbert space. It gives you element of the Hilbert space. Yeah, so now that we have matrices, being normalized means that the matrix has trace 1. We also want it to be Norwegian. Complex adjoint of the density matrix, density matrix, and it is positive sigma. This rho bigger equal to 0. And that simply means if I sandwich it vectors on the Hilbert space, this will give me a number, and this number is always non-negative, equal to 0 for all vectors. Oh, sorry, it's supposed to be the same vector. For all vectors psi in H. And then we denote the set of all these density matrices, so all the bounded linear operators on H that fulfill these extra conditions. It gets its own notation. Okay, so now like we somehow have two different kinds of ways to express the state of a quantum system. Yes?
Sorry, could you explain a little bit more the bracket notation that you use to define the density matrix? Yeah.
This one here?
Yes, please.
Yes. So we said like the cat denotes just a vector in the Hilbert space, right? And the right comes from the dual space. So this in principle is a map from the Hilbert space to the set of complex numbers. So you're building an object here that you can apply to a vector in the Hilbert space. So I can write here in principle some like vector phi of the Hilbert space, which means that this becomes the scalar product. So this will be some number in C. That means what comes out of this object is a linear combination of vectors in the Hilbert space. So in principle, this is like an operator on the Hilbert space in the sense you can apply it to a vector and it gives you out another vector.
And there, in the bracket notation is used again, but there's somehow 3
yes.
elements in it.
So here, what's happening, it says, okay, I have a vector in the Hilbert space, and then I apply this operator to the vector. So this is the application will give you some other vector psi prime in H, and then I take the scalar product with the state I started with. And I ask that this scalar product is always non-negative.
Just going back to this first question, can't we just see it like the product of column vector by line vector?
Yes, yeah, if I write it out as matrices, then
yeah.
Yes, this would be
the first one. Sorry.
line vector, and this would be a column vector. So this would be something like this would be a column vector. And then if you just do this multiplication, you see that you can get a matrix out of it.
But we're not always, we can work in an infinite dimension.
In principle, yes. Yeah, you don't have to restrict to finite dimension, but there's some. Not everything we do works in infinite dimensions well, so you can assume that everything we do is in finite dimensions, because I don't want to go into detail about the peculiarities.
Of affinity.
So the trace always needs to be well defined. Okay, yes. We have these two different ways of talking about the state of a quantum system, and I already said that density matrices, what they add in contrast to the pure states, is that we can also talk about insecurities about which state exactly it is in. Like if I specify this state, this pure state psi of my system, this means I know exactly the state. It might be a linear combination of pure states, but it's like I know exactly what state my system is in. And so historically, this is more the direction where like people come from when talking about like closed quantum system. Like you start with is your state in a specific system, and if you have a closed system, then any evolution will just give you out another concrete state of it. Okay, but once we see a quantum state more as a representation of the knowledge that we have about the system, then we need to add some like insecurities about the knowledge that can happen. That we don't always have perfect knowledge about what's happening with the quantum system. Okay. Good. So this is the quantum state. This is the object that we need. Sometimes we use pure states because sometimes just the notation and the calculations are easier. If we do it for pure states, then the calculations don't blow up as much. So for some examples, it's nicer. Okay. But this is the basic information that we need to know about quantum states. We can continue talking about the evolution of quantum states. attended a quantum theory course in your studies at some point, what you've learned about the evolution of quantum systems is most likely like the Schrödinger equation that tells you how the system develops in time. And this is something that we don't need here at all. So when we talk about the evolution of quantum systems, so the Schrödinger equation, first of all, it only works for like pure states. What it does, it gives you like it can tell you what the state of the system is at any time that you're interested in. And it can't really represent the like imperfect knowledge about the system. So what we're interested in is more, okay, I have a quantum state, something happens to it, another quantum state comes out. What is the relation between the two quantum states? So in quantum information theory, we're not really interested in like describing the state at any time step. We want to know, okay, there's some operation happening on the quantum state. How does it change my quantum state? So how we describe evolution of quantum states is typically we look at maps that take quantum states as an input and spit out other quantum states. And if you're interested in the timely dependence, you can add a time parameter to this map, but often it's not necessary because you're only interested in, okay, what's the output of this process? So what we need is a map. That maps quantum states to quantum states. I'll write down the definition and we will discuss the properties then. So this is a quantum channel. Is linear phase preserving map. Okay. So the fact that it's linear simply means that, okay, we call the quantum channel curl E. If I take a linear combination of quantum states, and this is the same as alpha times the map applied to the quantum state, this is the same times applied beta times the map applied to. Okay. Then we have the property, let me continue, it's trace preserving. So it means the output state of this map has the same trace as the input state. Trace the map applied to the quantum state is the same as the trace of the quantum state for all quantum states. Set of density matrices. This in particular ensures that my input state has trace 1, then the output state also has trace 1. So I always map to a valid density matrix. complete positivity part. Okay, first let's start with positivity. So a linear map is positive if the output state is positive semi-definite for all positive semi-definite inputs. This means the set of bounded linear operators, one Hilbert space HA, another Hilbert space HB, positive. The map applied to a quantum state is positive semi-definite for all positive semi-definite inputs, which is necessary again so that we get a valid density matrix out of it, because positive semi-definiteness is one of the properties this needs to fulfill. Is this sufficient to ensure that the output, is it sufficient to ensure that my map is well behaved? Can something go wrong if I only require positivity? Yes?
I guess you also need to be bounded. Because you could send your eigenvalues to infinity.
It's trace preserving already.
Yeah, I think that's already implied by the
Right.
linear trace preserving.
Right.
So, operationally, what can happen? Let's say we have the following situation. We have qubit A. And we have qubit B. Yes, there's some quantum state row AB that describes them. And we apply the map to qubit B. So this, here we apply the map, and we get out. And we do nothing to qubit A. It's like the identity. That means the output of this would be, and we're going to talk about this, so that on one thing we have to apply the identity, on the other the map. Okay. So if I ask positivity for my map, so I know that this map applied to qubit B, like on qubit B, it will behave nicely and give out a quantum state. But now I've added the identity on the other qubit to this. Will this still give me a valid quantum state? I think this is implied by the properties we have already discussed.
Necessarily.
In fact, one can find examples where even though this linear map, that as we have defined it here with being positive and everything, this one, it behaves nicely on this subsystem, but the composite map, connected with a map that does nothing on everything else, messes up your quantum state. Even though nothing happens on qubit A, the resulting quantum state is not, it's not a proper density matrix, even though this map fulfills positivity and trace preserving and everything. So that's what complete positivity captures. So resulting state component. So AB prime is not necessarily valid density matrix.
Question?
Yes.
What of these properties fails in this case? Or you can construct example where any of them can fail.
I think it depends on the example that you find. I mean, what fails is it will give you a density state that doesn't fulfill positivity anymore. This one fails. So even though you put in positive semi-definite quantum state, you apply this positive map on one part and the identity on the other part, the resulting state will not be positive anymore. So we need complete positivity, which just like captures exactly this scenario. This then is like the map is completely positive. So a map like linear map is completely positive if the map E tensored with the identity on like a Hilbert space as big as you would like it to do. You can add the whole world to it as long as you do nothing on it. This is the map. Goes from your Hilbert space of interest, say H, A, and Hilbert space complex with C to the power of N.
Are we assuming all the Hilbert spaces are embedded in CN, or not necessarily?
I mean, we're in finite dimensions here, so I think they're all isomorphic. This map is completely the map E is completely positive if this map is positive, which we have defined above, for all choices of n. So no matter how big you make this additional Hilbert space. And then you guarantee that we always get a valid quantum state out of this map.
Shouldn't the scalar product on the tensor space be just the product of the scalar products?
Yes.
To me it seems like
No.
immediately follow from like if I take the scalar product of identity and the quantum channel, then I get the product of like psi, which is positive.
But it's possible, like your quantum state is not necessarily a product state.
It's not separable.
No, not necessarily, yeah. Yeah, I realize, like, we haven't talked about the composite systems yet. We'll do that, then it's a bit clearer. Okay, but this is the definition of how an evolution is described. We actually not really require, we're not talking a lot about evolutions in this course. What we're more interested in is measurements and measurement outcomes. Yes, I make more space.
Example of like a state that breaks the positivity. I'm just struggling to see.
A prominent example for a map where this fails then is if you take the partial transpose, like your map is the transpose of the matrix, and that fulfills all the properties. You can check that. But if you apply, like if you then connect it with the identity on other parts, then it's the partial transpose. And that one can actually take a positive state and map it to a state with negative eigenvalues. Like the classical example people make in this case. So that's all I want to say about evolutions. Let me go to measurements. So now I want to describe what happens if we measure the quantum system. Measurement means we get some classical outcomes out of this process, and sometimes we also want to talk about the state of the quantum system after the measurement. Okay, so the question is, what exactly should measurement describe? Like, what kind of object do we want? We know we get some sort of classical outcomes, so it's clear that the measurement takes as input the quantum state, because that's what we want to measure. But then we can think about what are the properties that, like, what should come out of this measurement? So, our input is quantum state. And then for the output, what we're interested in is, so we have these classical outcomes. If we want to reason about these outcomes, again, what we're interested in is how likely are different outcomes. So what's the probability of seeing certain outcomes in our quantum system? The output is supposed to be a probability distribution. That depends on rho. For each possible outcome x, it gives the probability. So probability distribution p rho of x for the outcome. If you know that this is like, so it's some function of rho that spits out this probability distribution, then you can show that the proper mathematical object that captures these things is a positive operator valued measure. Called POVM for short. And so this is a set of operators with certain properties. So as the name says, they're positive operators. Elements are M index X. So there's one element for each possible outcome. Positive. Means on X. It's supposed to be and let's take a mx. I call complete. That means if I sum up all the elements in the set, I get the identity. We'll see in a minute why these properties are exactly what we require for the outcome to be a probability distribution. But first we need to specify how we get the probability distribution out of this object. So there are two questions I would like to answer when I look at the measurement. One is, what's the probability of the outcome? And the other is, what is the state after the measurement? Okay, so the first one is, so what is the probability outcome X? And that one we get X is given by the trace of the corresponding POVM element mx multiplied by the quantum state of our system called Born's rule. If my system is in a pure state, this is you can rewrite this as the operator with the quantum state. If you take this rule to calculate the probabilities, then you can see that we need positiveness of the operators, because if they're positive, then everything you get from this formula will be a positive number, which we need for probabilities. So this one guarantees that probability of x is non-negative. Then, if an operator is Hermitian, that also means it has real eigenvalues. That guarantees that, like, all the numbers you get here are also like real numbers. And lastly, the completeness of these operators guarantees that your probabilities that you get out of here sum up to 1. So you have a proper So actually, if you start with this requirement that your output is supposed to be a probability distribution and use this rule, then you can derive that this is exactly the object that fulfills these properties. I also said we want to talk about the state after the measurement, and this does not always work. Like, this is not always well defined, the state after the measurement. Only in specific cases, namely when we have so-called projective measurement. The special case is the projective measurement. Which simply has the additional property that the elements of the of this set are projectors. Delta ij. Then we can write on the post measurements. According to the following rule, so we have a pure state. Also, my post measurement state will be a pure state. Would be so if the outcome was x, then I get the the post-measurement state by applying the measurement operator to the original state and renormalizing this so that I get a normalized state out. Mixed state. The relation of this to mixed state is fine. And I have to normalize it. And this is basically everything you can ask the measurement to tell you. There's no more information that the measurement can give you. Okay. Yes?
What was the difference between a pure state and a mixed state?
So the pure state is just a vector in the Hilbert space, whereas the mixed state is an operator on the Hilbert space, so matrix.
Okay.
Yes, that's also why we apply the operator from both sides of the matrix. In principle, one of them has a dagger. I always forget which one, but since it's like Hermitian, they're both the same. Okay, so the most important example of a measurement that we need for the applications that we're talking about is how to measure a quantum system in a specific basis, like the computational basis or the Hadamard basis that we discussed. So that's what we're going to do. Fine.
Is there in the denominator of the pure state?
Oh. This is missing. Thanks. Okay, so I have a state on a Hilbert space, and I want to measure it in a basis of this Hilbert space now. So let's say we have a set of vectors which form an orthonormal basis. O and B on the Hilbert space. And we have one vector. So that be a vector in the Hilbert space. Then a measurement that corresponds to this basis, so we need to come up with these this PVM elements, and you can simply construct it directly from this basis element. So measurement on the basis PI is given by the PVM elements. Mi is take the cat pi and the bra. This, if I think about this as like vectors, and this will give me a matrix that I can apply to the vectors I want to measure. And you can like check that this fulfills all the properties that a positive operator value measure has to fulfill: positivity, Hermitian, and completeness, because it comes from a basis. And this is even a projective measurement. And see if we take IMJ, and just write it out. And here you have a scalar product between two basis vectors. So this gives you the delta J. And then you have the prefactor of a basis vector into bra, which is exactly how these are constructed, and it's only non-zero if you have the same vector. So this is the important examples that we need in terms of measuring the bases are the ones that we introduced in the beginning, the computational and the Hadamard basis. So do that basis. So 0 and 1. It means we only have two POVM operators. It's very easy to set up this measurement. And then you can look at, okay, if I have a general quantum state, a general qubit state, that was just combination of 0 and 1. Then I can use the formulas that we had to calculate, okay, how likely is it to see a 0, how likely is it to see a 1. So if you then you calculate this into a pure state, we can use the formula for pure states. It would simply be 0 psi, the measurement operator is 0 psi. So you have to put in like all the states in the operator. So what you would get is alpha 0, beta star 1, and the measurement operator is again like this. Then you can write out all the combinations. So whenever a 0 meets a 0 in the scalar product, you have a 1. Whenever 1 meets a 0, you get a 0. So in the end, out of this is alpha star times alpha, so the absolute value of alpha squared. So this prefactor of the 0 in the general state just directly gives you the probability of measuring 0 if you measure in the spaces. And similarly, you will see that probability of 1 is and now it also makes sense that we're interested in normalized vectors in the Hilbert space, because the normalization exactly like was that the absolute value of alpha squared plus the absolute value of beta squared equals 1, which means that these probabilities for different outcomes sum up to 1, so they give a proper probability distribution. If we had like states that are not normalized, then these outcome probabilities will not give you a proper probability distribution. Okay. Well, and then the same thing that you could do is to set up the measurements in the plus and minus. Done with all the ingredients from quantum theory that we need. The last thing that we need to talk about is what happens if you have like not one quantum system that you described, but a composite system of two or more quantum systems. similar to when we define, okay, what happens if there are two random variables instead of one, and then we describe them simultaneously. So that's the last subsection quantum possible. Basically, you want to describe the two quantum systems, so A and B. System A is in some state psi A, B is in some state psi B. And you want to describe them simultaneously with one quantum state that captures both of them. So the quantum system AB. You want to say, okay, how does the state AB look like? It's very simple if I already know the exactly the individual states what A and B are in. So the mathematical object we need is the tensor product of Hilbert spaces. So a composite system. Hilbert space HA, Hilbert space HB. Then my Hilbert space of the composite system is simply the tensor product of HA and HB. So if I know that my individual systems are in these pure states, then I directly know that the state of the composite system is the tensor product of the two individual states. And you can also simply get a basis of the joint Hilbert space by using the tensor product of the basis states of the individual ones. Basis. I have a basis on A, and a basis F, J, and C. Then get a basis of the composite system. By taking all the tensor products. That also shows that the dimension of the composite space is simply the product of the dimension of the individual ones, because just from the construction of the bases we can see that. Maybe to make one explicit example, then we need. So, example, if I take two qubits, let's say both have the same basis, just the 0, 1 basis, so take 0. Construct the basis of the joint system by simply taking the tensor product of this. And now if you haven't seen a tensor product in a while, I will just remind you how you calculate that. So the basis for, let's call them HA, HB. We take all the possible tensor products of this. 0, 10, 0, 0, often don't write out these tensor products explicitly if it's clear. But to make the notation shorter, just say 0, 0, 0, 1, 0, 1, 1. Which is also some form of like data compression, because I use the short notation for a longer one, but you're still able to recover the exact mathematical meaning of this. And then if you like want to calculate one of these vectors, for example, 0, that would correspond to, say, this is the first 0, 0, and the second vector. And we calculate this, and you get a larger vector out of this. I get it, you take the first vector, 0, multiply this to both elements of the second term. So what you get out of this in the end is 1, 0. Just to remind you how this actually works to calculate the vectors for the tensor product space. And then as you can see, like this structure hints at that the rest of the bases will continue this structure. So you see, if you calculate this, like the next one, you just move the 1 around. Exactly like you would come up with a canonical basis for a 4-dimensional Hilbert space. And then the general quantum state in this 2-qubit space would just be a general linear combination of these basis vectors. So, yes, so this is like how you can construct these bases. And of course, the interesting part about this is that you don't only have these product states. Let me quickly say, okay, for density matrices, this works like very similarly. Like if you know your quantum states row A and row B, then you can get the joint quantum state row AB by a tensor product of the two states. Yeah, but the fun part about this is that there are more states than product states. And there are states that you cannot simply write as a product of two individual states of these systems, but they have a more general form, and in particular they capture then more general correlations between the quantum systems. And that's where a lot of the fun applications of quantum information theory come from. I'll just in this section the definition for these states. Interesting part. There are more states in this Hilbert space. And B than product states. For example, we can take a linear combination like this. 0 and 0 plus this is a linear combination of product states, but I mean, no matter what you do, you will not be able to write this as a like product state of one state tensor the other. Even like yeah, you can like try it if you like, but there's no way to get a product state out of this. And these types of states are called entangled state. So we'll end this lecture with just the formal definition of entanglement. So a pure bipartite state, so state for two joint systems, psi on A, B. It's called entangled. If it cannot be written as a product state, and B for any choice phi and otherwise it's called separate. And for mixed states, you can get an analogous definition. So you just have to the mixed states state is a bit more general than just the product of two mixed states, but a linear combination. So mixed state. So linear combination. Well, this is some probability distribution. So the entangled state is one that cannot be written as a linear combination of products. So this concludes all the like basic machinery that we need in like information theory and quantum theory to look at interesting applications of that. Yeah.
Just a quick question: can you not write this in the tensor product in this form?
No.
Because she's restricting to positivity, so PFX has to be positive.
Yes, so PFX has to be a probability distribution, and these have to be density matrices, not just any matrices.
Okay. Oh, yes. Okay. Okay.
You can write it as this if you like just say, okay, just take any matrix. Yes, then it works. But these specifically have to be density matrices. Yes. Okay. So there's an exercise sheet for you that is on the website of the summer school, where we put these things that I've introduced here to use. So there are some like interesting applications of all these concepts that I introduced now, so you can see how things work a bit. So if you have some time, look at it, see if you can do the calculations. It will give you much more intuition about why these concepts and objects are interesting that we have now introduced. And we will discuss the exercise sheet and this exercise in the next lecture. And then we'll continue with like more interesting applications. So today we covered like all the basics, so there's a lot of definitions. But then the rest of the lecture we'll kind of look at the consequences of these concepts and definitions and see what fun things we can actually do. Okay, and have a nice lunch.